Hello, and welcome. Today we're going to be talking about star formation, specifically the gene's instability. So the idea is, in this video, I'm going to give you a general overview, and the back of the envelope calculation of the gene's instability. And in future videos, I will be discussing some more things about it. I'll be deriving it in its formality, and I'll be talking about the gene swindle and how he swindled us. Maybe I'll do some examples and I'll write some code to actually calculate this. Anyway, without any more ranting on, let's get into it. So what's the idea, right? This is kind of like the first stage of star formation, which is you have a giant cloud of gas, right? And let's assume this gas starts out in equilibrium. It's not collapsing, it's not expanding. And your question is it going to collapse or not, right? Because what happens is you have this giant cloud of gas. I'm moving my hands around and I know you guys can't see me moving my hands, whatever. So you have this giant cloud of gas. And the what happens is gravity will kind of force it to collapse in on itself, and that's how you form stars, from this collapsing gas. And so, that's the question. Is this giant molecular cloud of gas going to collapse or not? So let's do a back of the envelope calculation of this and see what happens. So here's kind of the idea. The thing that's causing the cloud to collapse is gravity, right? It's the force of gravity. So there's a whole bunch of mass inside here, of course, and that's forcing everything to collapse in. But what's the thing pushing out against that? The thing pushing out against that is pressure. So you have pressure pushing outwards, and you have gravity pushing. So you're pulling inwards. There we go. And so these two forces are kind of fighting each other. Now, in hydrostatic equilibrium, which is our assumption, you have the force of pressure and the force of gravity are cancelling each other out. But we want to know, is this stable or not? And the idea is we can look at the time scales for which pressure can move things versus the time scale for which gravity can move things. So like the kind of idea is here. Imagine, okay, it's in perfect hydrostatic equilibrium. Imagine your gas cloud is perfectly uniform, perfectly smooth. Hydrostatic equilibrium, we're all happy. But then let's say I make like a small perturbation over here, right? Make it a bit denser over here. Or, I perturb it like, like a sinusoidal, basically the idea is I change the density in some region. Well, what's going to happen is gravity is going to want to collapse in on that, right? And so what's the timescale for gravity to act? That's called the free fall timescale. We'll derive this in a second. And then the question is, how long will pressure take to smoothen out that density, right? Because that's what's going to happen. Gravity is going to want to make that more dense, while pressure is going to want to make that less dense. It's going to want to smoothen it out, distribute over the whole cloud. And that's given by the crossing time, right? And so the point where this situation is marginally stable, meaning, if you make it any bigger, it's unstable. If you make it any smaller, it is stable, is when these two timescales are equal. So that's going to be the idea of this derivation, and we're going to do really back of the envelope order of magnitude estimates. In future videos, we'll do a very formal derivation of this. But here's the idea. So what is this free fall timescale we're talking about? Well, it's a timescale for a little blob here to fall inwards, really, to cross over like this. Now, you can do a really formal derivation of this. What we're instead going to do is, once again, order of magnitude estimates. So we know that it'll probably fall on roughly the Keplerian timescale. So the idea is this, right? If you have a body here, say here's the sun, and you're orbiting the sun. Oh wow, that was a terrible orbit. Oh wow, okay, I can't draw, it seems. So the idea is you will orbit at some speed, and that's p squared is equal to 4 pi, your distance here, we'll call it r cubed on g mass of the sun. Okay. And the idea here, and this should be 4 pi squared, I believe. So the idea So this is how long it takes to take one orbit around the central object. But what you can do is you can stretch out that orbit to make it as uncircular as you want, basically, make it elliptical. Um, and you get the same formula. It's the same thing. It only depends on this distance r. Well, it's not your absolute distance called it's part of it's the semi-major axis, basically. Not basically, it is. So that's the idea anyway. So what we can do is we can just use this formula to get our freefall timescale. So timescale freefall goes as 2 pi r to the 3 on 2 over square root of gm. And now m is the mass of the cloud, r is the length of the cloud. Perfect. So we got one formula here. Circled that. Now let's look at the crossing time. How long does it take for pressure perturbations to move over that region, right? To move that throughout the whole cloud. Well, that's given roughly by the time it takes for a sound wave to cross from one side of the cloud to the other side of the cloud. So we know velocity is equal to distance over time, implying time is equal to distance over velocity. Distance is the length of your cloud, call it r. Velocity is the sound speed. That's like by definition how fast the sound wave travels. So r over sound speed. So now we have our two timescales. Crossing timescale is roughly your cloud length divided by the sound speed in your cloud. We're assuming this cloud has uniform density, so uniform sound speed throughout. Same thing with the freefall timescale. So now we have these two timescales. All we have to do is compare them. So let your freefall timescale equal your crossing timescale. And now instead of r, we're going to be using lambda j. That's the gene's length. So you get 2 pi gene's length to the 3 on 2 over square root of gm equals r on sound speed. I really shouldn't be saying r here. As I just said, we're going to be using the gene's length now. It's no longer r. So gene's length. Okay. Now, if we rearrange for the gene length, sorry, I wish I knew how to cut and paste, but we're going over here now. So this implies the gene length. Divide by 1, you get 1/2 is equal to square root of gm on 2 pi sound speed, implying gene's length is equal to gm on 4 pi squared sound speed squared. And that's your gene's length. So cool. What does this actually tell you now? The idea is this. If your cloud's length is greater than the gene's length, then your cloud will be unstable. Okay. And you can think about it like this. I have an idea for this. Give me 1 second. So imagine you're imagine that you're like the tiny little island of Tuvalu. Let me look this up. Tuvalu. Can I see it on maps? I can. So imagine you're this tiny, I know this is going to sound weird. Okay, no, we got this. So imagine you're this tiny little island of Tuvalu and, you know, something happens over here. Bar fight happens over here. Well, your police are going to be somewhere nearby, right? So you're going to be able to suppress that thing. It's kind of the same thing with this cloud, right? If your cloud is really, really small, you get a small density perturbation, well, your pressure is going to be able to just smoothen that out pretty easily. But if you're, on the other hand, the Roman Empire, if on the other hand you're the Roman Empire, right? And say something happens in Spain over here, right? And say you're all the way over here. Well, if something happens, it's going to take you a long time to sort that out. It's going to take you a long time to get there and smoothen out the issue. And it's the same thing. If your cloud's really, really massive, if you get a if you get an over density somewhere, then it's going to take a long time to smoothen that out. So that's the general idea. And I should say in this formula, m is the mass of the cloud, sound speed is the sound speed of your cloud. So that's the general idea. So your length is greater than your gene length. Then that means that you are implying you are unstable. Okay, now what a lot of people talk about is this thing called the gene's mass, and that's pretty easy. Just assume that your cloud is a uniform sphere, so it's a volume of a sphere 4 pi on 3 gene's length cubed. So that's the volume of your sphere times the density of your cloud, and you just plug in the numbers, spits you out an answer. And that's what the gene's mass is. So that's the general idea. And now the question is, what actually happens with a cloud? Well, what's actually going to happen here? And the idea is this. I'm going to draw a diagram for you here. So this is log density. This is log temperature. You know, it might be actually informative if I went through the steps here more properly. So let's do that. So actually one thing I completely forgot about is typically the way this is actually defined is it's defined so that it's not actually the gene's length, it's the gene's length on 2, because the gene's length is the full length of your cloud, it's the diameter, but really this formula is the radius, so this should be gene's length on 2 cubed. Okay, so the idea now is if you just plug this in, you end up getting this is equal to pi on 6 rho lambda j to the 3, implying your gene's mass goes as rho lambda j to the cubed, and really we can get the dependence on we kind of want the dependence on sound speed. That will be useful. So lambda j is proportional to sound speed to the -2. So that's proportional to rho sound speed to the -3 on 2. Okay, sorry for messing you around a bit here. I'm actually going to rethink about the way I do this. So yes, the gene's mass is fine. But let's kind of rearrange this gene's length to be more obvious. So yeah, let's rethink about how to do this. So the gene's length, as I said before, I'm going to remove the factor 4 pi squared. It's fine. Is roughly goes as gm on sound speed squared. Okay. Now mass, right, goes as rho lambda to the cubed, right? Because this is your length. This is your density. So this is volume times mass per unit volume. This just gives you a mass, right? That means lambda goes as g rho lambda cubed on sound speed squared, implying lambda j is roughly squared sound speed over square root of g rho. So lambda j is proportional to sound speed rho to the -1/2. Now, your mass is given by what we had up here. So mass goes roughly as, so your gene's mass goes roughly as lambda j cubed rho, lambda j cubed times rho. So finally, this gives us the gene's mass roughly goes as sound speed cubed. Rho times rho to the minus 1/2 just gives you rho to the, sorry, okay, so you have rho to the minus 3 on 2 times rho, which is equal to sound speed cubed, rho to the minus 1/2. So this is kind of what we want to look at. Now, we can also probably rewrite this in terms of sound speed. Okay, we'll worry about that in another second. So I think for now we will stop. Here are the formulas. So here's the gene's mass. Here's the gene's length. And in future, we're going to talk about, actually, you know what, let's talk about it now. Let's talk about what happens with a collapsing cloud. So you have log density, you have log temperature. So what's going to happen when the cloud first starts collapsing is it's going to be able to radiate the energy away as it collapses. So you're going to get some sort of constant temperature. And then at some point you're going to start trapping in radiation, right? Radiation's not going to be able to escape, so the gas is going to start heating up. Maybe in future videos I'll talk about exactly how you get this, but you find the adiabatic index is 7 on 5, right? And at this point here, what's going to happen is, as the gas collapses, it becomes more and more unstable, and you end up getting different overdense regions which become more and more unstable, and the stability criteria shrinks, and you start getting this fragmentation, right? So it's not this nice clean spherical collapse all into a single star. What you get is a whole bunch of different collapsing regions which are all going to be forming a whole bunch of stars, right? And then after, so this is all for molecular H2, right? But then what happens, at some point the temperatures get hot enough where H2 starts to dissociate into H1 plus H1. And then the adiabatic index is going to change again, and you get gamma is around 1.1. And then finally, once all the H2 is disassociated, you end up getting, once again, a steep region, gamma equals 5 on 3. And yes, and that is where you form your first protostar. So I think in a future video, I will probably derive this and talk about this more. And I'll probably give an example on how to calculate gene's mass and gene's length. But for now, here's a rough back of the envelope calculation. And in future, we're going to do a more formal derivation. Thanks for listening.